I found this nice cartoon in Republic of Math which sort of depicts the state we are presently in. So, what we are doing is we are doing a lots of calculations, humongous amount of calculations, right. In fact, so humongous that we are not even doing it, at least I am not doing it, I am telling you that you can do it by yourself, right. Tedious big calculations, but I mean if you are intimidated, we are intimidated only by the volume. The tools are not all that difficult so far. What is present in this cartoon is looks much more intimidating. So, but then this is leading us to very important results, that is why we are happy like this person right here. Okay. What we want to see is, can we now slowly move towards a situation where this boat full of mumbo jumbo falls into something that is systematic and easier to handle. Okay. So, to do that we once again recap what we have learned. I will not say once again all these h psi equal to E psi kind of thing, but we have studied upper limit theorem, we have used it, and I will show you the results once again to refresh your memories. For hydrogen atom, using upper limit theorem, we have calculated an energy, and the peril of copy paste, the second equal to sign is still there. We have obtained a value of 0.424, whereas the actual value is 0.5 with minus sign for hydrogen atom. For harmonic oscillator, we have a deviation of about 14%, and for particle in a box using a weird wave function, we have got a deviation of about 4%. So, the strategy is, or the features that we have seen so far is, we start with an arbitrary trial function, arbitrary in the sense that we do not know whether it is the correct one, but then there is a method in the madness as well. We remember what we did for particle in a box or for simple harmonic oscillator, we sort of realized that they have to be symmetric with respect to the midpoint, and they have to become 0 somewhere or the other. So, I am not going to use something like e to the power alpha x square, that is not even a good wave function. Okay. So, when I say arbitrary trial function, it is arbitrary within a certain limit. Okay. It is not arbitrary completely using anything, that is not going to work. Okay. You still have to think before you decide which trial function you can use. Okay. So, we have to guess the nature depending on the system, and this trial function has to be associated with variational parameters, means parameters that we can vary and see how that variation affects the energy of the system, and for which value of this parameter or parameters we get the minimum value of energy. Okay. So, the more parameters we use, and this is something that we will demonstrate today, we will get closer to the correct result. Of course, the downside of that is that the calculation becomes more tedious. Okay. But then if you have sufficient computational power, it is better to use as many parameters as you can. There is no problem of over parameterization, we are saved by the upper limit theorem. Great. So, what we will do now is we are going to use this trial function, which is a linear combination of functions. Okay. So, let us say that we express this function of ours phi, which is the wave function of the system, as a linear combination of n number of some arbitrary but known functions. Are they orthonormal? Not yet, and at the risk of boring you, I am going to say this 3-4 times more. Please remember, right now we are performing a perfectly general discussion. Okay. We know what the functions are, they can be Gaussian functions with different full width of maximum and curvature and so on and so forth. They can be cosine functions, sine functions, combinations of them. Okay. But I should know the functional form of f at least. Okay. It is not completely arbitrary and then everything will converge at the end, no, that will not happen. So, I start with capital N number of arbitrary known functions which are compatible with the system, and what I do is I use the coefficients as the variational parameters. Okay. We can always do it, and again this is something that we have encountered in chemistry. I am not sure whether I have referred to it earlier in this course, but even if I have, I will do it again. See, I request you to think of something that we studied in solutions, in the chemistry of solutions, thermodynamics. Remember, we talked about activity and we said that concentration usually, especially for more concentrated solutions, concentration is not a good enough parameter, you have to use activity. Activity is equal to concentration into activity coefficient, right. So, the thing is this, what does that mean? So, we are pretending as if part of the concentration, actual concentration is not available for doing the reaction, right, because law of mass action says that whatever mass of the reactant there is, that is going to participate in that reaction, that is going to govern the rate of reaction and so on and so forth. Why are we using a fraction of the mass by invoking this activity coefficient? Because the problem is not with concentration, to be honest. The problem there is that these ions especially cannot move as fast in solution in the presence of other ions as they would in their absence. So, consider sodium chloride solution, this is a sodium ion and there is well one excess of chloride ion around it, right. So, now when the sodium ion moves, it has to overcome the drag by the what do we call negatively charged cloud, okay. That is why it is actually running slower, but since we do not have any easy way of handling this running slower business, we use this coefficient and pretend as if not all of the concentration is available for doing the reaction, right. Similarly, it is very highly possible that actually you should play around with the function itself, like what we did earlier for particle in a box. Remember, we had this x to the power alpha kind of thing. Perhaps that is the right thing to do, but we do not know what the right thing to do is. So, we just compensate for that like we did for activity in case of activity and activity coefficients. We compensate for that by bringing in this coefficient for each of these functions, and we say that this coefficient is the variational parameter. So, basically we make this problem a mixing problem. When I take a linear combination, it is as if I am mixing functions, right. I cannot mix functions with hand, but I can add them, right. I can. So, coefficients tell me what is the contribution or concentration of each function in the function that I synthesize. So, I am playing around with the composition of the function by setting Cn to be the variational parameters, then we can use with we can work with fixed functions Fn, right. So, and we will see an example of that when we talk about this particle in a box problem. And to keep things simple, we start with real coefficients, but that is really not mandatory. You might as well work with complex coefficients, it will take care of itself. And also to keep things simple, we start it with a 2 component system. Let us say only 2 functions contribute to phi. So, n equal to 1 and 2, right, capital N equal to 2. In that case, what is phi? Phi then will be equal to C1F1 plus C2F2. Okay. What is F1, what is F2? It is something, I have decided that this is F1, that is F2, I have not revealed yet, and phi is the wave function I try to synthesize. Okay. So, now this is what we want, right, epsilon 0. How do we get it? Let us try to evaluate the numerator first. Integral phi star h phi, is h known? Yeah, h would better be known for a system, right, h is known. So, what I do is in ket vector bra vector I write C1 F1 plus C2 F2, which really means its complex conjugate. In the ket vector I write C1 F1 plus C2 F2 itself. And now I have 2 terms in the bra vector, 2 terms in the ket vector. So, I am going to get actually if I open it out, I am going to get a sum of 4 different integrals multiplied by appropriate coefficients. Let us see. Let us take the first term of the bra vector, first term of the ket vector. What do I have? C1 F1 left multiplying H operating on C1 F1. So, since H is linear, C1 is going to come out and I am going to get C1 square outside the integral. Inside the integral I have integral F1 star H F1, this C1 square multiplied by integral F1 star H F1. Okay. So, this is the first term I get. What is the second term? The second term I can take between this first term of bra vector and second term of ket vector. If I do that, I get C1 from bra vector, C2 from ket vector, F1 in the bra vector, H operating on F2 in the ket vector, right. Next I take the product of C2 F2 and H C1 F1, then I get again C1 C2, it does not matter whether I write C1 C2 or C2 C1. So, I will follow the same convention multiplied by integral F2 star H F1 star, sorry not F1 star, F2 star H operating on F1. Is there anything else? Yes, there is something else. C2 F2 multiplied by H C2 F2. So, I bring that C2 out and we get C2 square multiplied by integral F2 H F2. Okay. So, see the first and the last integrals are similar in form, they are integral Fi H integral Fi star H Fi, right. In the first case I equal to 1, in the second case I equal to 2, that is all. So, this I call H11 and the second one is called H12. So, in general I can call these the HII vectors. In the case we are discussing, I can take up only 2 values, I equal to 1 or I equal to 2. Okay. So, this is what we get, HII. Next we focus on the other 2. Well, you understood where this I11 came from, right. The index denominator, well not denominator, index or subscript of the function. Here in the bra vector you have F1, ket vector you have F1. So, one from here, I call it H11. Here you have 2 in bra vector, 2 in ket vector, so H22. So, what will this one be? We have F1 in bra vector, F2 in ket vector. So, this will be H12, this will be H21. Okay. Before I forget, let me remind you that these are actually matrix elements. If you write an H matrix with these integrals, then H11 takes the 1 position, H12 takes the 1 position, H21 takes the 2 position, H22 takes the 2 position. Okay. So, these are matrix elements. Since I have forgotten to write this here, let me at least write by hand. So, these are matrix elements, forgive my bad handwriting. Okay. So, now let us quickly write an expression for integral phi star phi d tau. Yeah. So, again substitute C1 F1 plus C2 F2 for phi in both bra and ket vector, open them up, this is what you get. Once again you have C1 square multiplied by, we call this S11, integral F1 star F1 we call it S11. This integral F2 star F2 d tau is called S22 and these two are called S12 and S21 respectively. Now this S, does it ring a bell? I mean I am sure most of us would have studied some quantum chemistry course somewhere. When we talk about bonding, this kind of expressions are often encountered and this S is used for overlap integral. Okay. please remember that these are not overlap integrals here, because when you talk about overlap integrals, the convention is you talk about two different atoms. Here we are discussing the same system, okay. We are not even talking about an atom or anything right now, okay, same system. So, let us just call this S11, okay. They are going to evolve into overlap integrals later on when you talk about molecules. So, we have ended up, and once again do you see that S11, S12, S21, S22, they are again matrix elements of the capital S matrix, okay, not very difficult to understand. So, it is trivial and it is very easy to see that S12 has to be equal to S21, yeah. It should also be very easy to see that H12 equal to H21. Why? Because we know turnover rule right now, right. So, we can easily write integral F1 star H phi 2 is equal to integral F2 star H phi 1. Remember, H is a Hermitian operator. Even though we do not know what the wave function is, we know what H is, and even if we do not know what H is, H has to be a Hermitian operator by definition. So, turnover rule is applied and H12 is going to be equal to H21. So, that is an important observation. In the H matrix, the corresponding off diagonal elements are equal to each other, okay. H31 equal to H13, H23 is equal to H32, so on and so forth, okay. So, if you substitute this, what do you get? C1 square multiplied by H11 plus C1 C2 multiplied by H12 plus H21. So, H12 and H21 are one and the same. So, I get 2 into H12 or 2 into H21 is fine, that multiplied by 2 C1 C2 plus C2 square multiplied by integral F2 star F1 sorry. What am I saying? Okay, I will just say that once again. What I am trying to do is I am trying to write an expression for epsilon 0 phi. While doing that, I am just simplifying it and we are writing this expression here. I get C1 square multiplied by H11 plus C1 C2 multiplied by H12 plus H21 in brackets. Since H12 and H21 are one and the same, I can write 2 C1 C2 H12 and the last term is C2 square multiplied by H22. One thing I want to remind you is that these are numbers, are not they, right. These are integrals and they are integrals that we should be able to evaluate. We are going to choose the functions that way. So, these are all numbers, okay. The coefficients are actually the parameters here. Similarly, in the denominator I get C1 square S11 plus 2 C1 C2 S12 plus C2 square S22. Now, what we will do is just to get into the same convention as that of the textbook, I am going to write I am going to replace epsilon 0 phi by E. So, I get E multiplied, so I am basically bringing the denominator up in the numerator of the left hand side. So, E multiplied by C1 square S11 plus 2 C1 C2 S12 plus C2 square multiplied by S22, okay. C1 square S11 plus 2 C1 C2 S12 plus C2 square S12. This is your left hand side. Right hand side will be equal to same as numerator C1 square multiplied by H11 plus 2 C1 C2 H12 plus C2 square multiplied by H22. What do I do next? What do I want to do? I want to find the minimum value of energy. For that, I have to differentiate with respect to the variational parameter and equate to 0. So, when I differentiate left hand side equal to 0, what do I get? I get two terms essentially, right. It is a differentiation of product, remember. So, in the first term I am going to differentiate this function and in the second term I am going to keep the function intact and differentiate with respect to E. Sorry, so I differentiate with respect to alpha all the time, gamma what is the parameter, sorry, C1 all the time. Since it is a differentiation of products, first of all I differentiate this function that I have keeping E constant, then I differentiate E with respect to Cn keeping the function constant. Okay, I hope I did not confuse you too much. So, when we differentiate with respect to C1, what do we get? With C1, right. So, first of all let us keep E and differentiate this function here. So, I will get, and I am differentiating with respect to C1, right, everything else is constant. So, here from here the first term I get 2 C1 S11, in the second term dC1 is equal to 1. So, I get 2 multiplied by C2 multiplied by S12, 2 C2 S12. Similarly, what I can do is I can do the other part, second term. There I do not have to differentiate the function, I have to differentiate energy. So, when we do that we get del E del C1. Here I have to write del because there are 2 parameters C1 and C2. So, what do I do? I just expand it a little bit first, it is equal to 2 C1 H11 plus 2 C1 H12. So, I am now differentiating the right hand side. So, now see, are you convinced that I differentiate the right hand side? C1 square H11, you differentiate with respect to C1, what do I get? I get 2 C1 multiplied by H11, and remember what I said, H11 is a constant, right, it is a number, plus how do I get 2 C2 into H12, because we are differentiating with respect to C1. So, this becomes 1 and we are left with 2 C1 H12. Okay. Now, what about the third term? Third term is C2 square multiplied by H22. With respect to C1, C2 is constant, H22 is a constant anyway. So, we do not worry about it, it becomes 0. Moreover, if you want to find the minimum, then this del E del Cy has to del C1 has to be equal to 0, right. So, we set that to be 0 and this is what we get. I set this to be 0. So, this entire second term becomes 0. Maybe I will just cut it out and see what happens. So, since this is 0, I just cut it out. So, now I have something on the left hand side, E multiplied by 2 C1 S11 plus 2 C2 S12 equal to 2 C1 H11 plus 2 C2 H12. I can collect the terms in C1, can't I? Let us do that. So, we can write E multiplied by 2 C1 S12 plus 2 C2 S22 is the same thing, plus this is equal to 0. Sorry, what am I doing? I think I have got the animation wrong, sorry about that. Okay. So, you differentiate with respect to 0 and then this is what you get, right. You just bring it to this side. What happens? Everything is multiplied by 2, so 2 cancels. So, C1 multiplied by H11 minus E into S11, this is what we get here, and we could have put a minus sign in front of that, it would not have changed, it is equated to 0 anyway. Then terms in C2 would be, we are bringing to right hand side, remember. So, C2 multiplied by H12 minus C2, well H12 minus E S12, right. that is what the coefficient of C2 is on the left hand side, C2 multiplied by E multiplied by S12, alright. So, from there we get this linear equation in C1 and C2. Remember, C1 and C2 are variables. Now, I have 2 variables and so far I have only one equation, I need one more. I obtain the other one by differentiating with respect to C2 and equating to 0, keeping in mind that del E del C2 is 0 anyway. So, from here it turns out to be 2 C1 H12 plus 2 C2 H22, that is your second equation in C1 and C2. What can I do from here? First of all, I can try and focus on the coefficients and try to find expressions for the coefficients, right, because the simultaneous equations are in terms of C1 as variable, C1 and C2 as variable. The problem with that approach is that I do not know E yet. So, better find out E first. Okay. Let us learn that and then I will tell you that you can of course go ahead and find the coefficients, but we will not do that in this course, that is all, but it is very simple. Alright, so here we are, we have got an equation, right, we have got an equation and I hope it is not difficult to see that we can write it nicely as a matrix equation, where the matrix elements are not H11, S11, so on and so forth, no, rather they are H11 minus ES1, H12 minus ES12, what did I say, H11 minus ES11. The second one is H12 minus ES12, third one is H12 minus ES12, fourth one is H12 minus ES12. That is the matrix. Now, what are the possibilities now? One possibility is that C1 and C2 is equal to 0, then we do not have to worry about it. The problem is if C1 and C2 are equal to 0, then what are we talking about here? Then I do not have a wave function. No matter what f1 and f2 may be, if C1 equal to 0, C2 equal to 0, the function vanishes, phi does not exist, it becomes 0 and a wave function cannot be 0 everywhere, that is one of the things that we learned from Born approximation. So, the other option is that this matrix equal to 0. So, if you go a little further using Cramer's theorem and all, what it turns out is that this secular determinant means the same matrix elements make up a determinant this time, that is equal to 0 in order to have C1 C2 is not equal to 0. Okay. What is the variable now? In this case H11 I can find out, S11 in principle I can find out, the only variable here is E. So, if we set that secular equation to be 0, then we are going to get an equation in some nth order. Do we agree that, well, here in this case we are going to get an equation of second order quadratic equation. So, if we solve these, we will get 2 roots, 2 solutions. So, we use the smaller ones, we first of all of course evaluate the roots, and the root with lowest energy is the ground state energy, because there can be nothing with energy lower than ground state, is not it. So, that is what we get. Fine. So far for so much for secular equations for now. Well, not really, I want to show you the general form. The general form is for n number of terms, this is what you will get, H11 minus ES1, H12 minus ES12, why am I saying ES1 all the time, H11 minus ES11. The 1-2 term is H12 minus ES12 and so on and so forth up to H1n minus ESnn 1n. In the second term everything remains same, just this subscript 1 becomes subscript 2, so on and so forth until in the capital Nth row this subscript becomes capital N, right, okay. So, this has to be equal to 0, this is the equation that we need to solve. So, let us break now and let us come back and discuss very quickly in a short module how to tackle this particle in a box problem using secular equations.